Conditional expected value. Suppose I roll a 6-sided fair die, repeatedly until I roll a 6. Let x denote the number of rolls that it takes me to roll a 6. Then, for any k greater than or equal to 1, we have the following probability. The probability that it takes me k rolls to roll a 6 is 5/6 to the power k minus 1 times 1/6. This is because there is a 5/6 chance that I roll a number that is not 6. It is taken to the power k minus 1 because that is how many times I roll a non-6 before I finally win and roll a 6. And there is a 1/6 chance that I roll a 6 and finish this very boring game. Based on this, we can say that the random variable x has a geometric distribution with probability 1/6. Let's try another example. Suppose this time, we roll the die exactly 12 times. Let y be the random variable that denotes the number of 6s we roll during these 10 trials. For k between 0 and 12, the probability that I roll exactly k 6s is 12 choose k multiplied by 5/6 to the power 12 minus k, times 1/6 to the power k. 12 choose k is for all possible combinations of rolls with 6s and non-6s within the 12 trials. 5/6, the probability of rolling a non-6, is taken to the 12 minus k power since k denotes the number of times I roll a 6 in this scenario, so 12 minus k is the number of times I will roll a non-6. And again, 1/6 is the probability of rolling a 6, taken to the power k, which is the number of times we roll 6. As a result, we can say that the random variable y has a binomial distribution with 12 independent trials, with probability of success being 1/6. Now suppose I roll the die repeatedly until I've rolled 4 6s and then stop. Let z denote the number of rolls this takes. Since we need 4 6s, we can restrict k to be greater than or equal to 4. The probability that it takes me k rolls, which is at least 4 rolls, is k minus 1 choose 4, minus 1 multiplied by 1/6 to the power 4, times 5/6 to the power k minus 4. We take k minus 1 choose 4, minus 1, to calculate all possible ways the first 3 6s can be rolled. Remember, the last 6 is also our last roll since the game ends after that. 1/6 is taken to the power 4, since 6 must be rolled 4 times for the game to end, and 5/6 is taken to the power k minus 4, for all the remaining times a non-6 is rolled. In this case, the random variable z has what is called a negative binomial distribution with 3 6s that fail to win the game until the 4th success with probability 1/6. So when there are no failures before the first success, we can see that negative binomial distribution is just a geometric distribution. Let me put forth a problem to you. Say I roll a 6-sided die until I get a 6 and then I stop. This is just like in the first problem. Now let me throw something new in. Let a denote the event that during the process of trying to roll for a 6, I never roll an odd number. What is the conditional expected value of x given that event A occurs? In other words, how many rolls does it take on average to roll a 6 if I only roll even numbers? To do this, we need a definition. For a discrete, non-negative random variable x, and an event A with the probability of event A occurring is greater than 0, the conditional expectation of x given that A is defined to be the sum over all possible values v of each v times the probability of x being value v, given event A occurring. For any discrete random variable x, though not necessarily non-negative. If the expectation of the absolute value of x, given A is finite, then we can also define the expectation of x given A in the same manner. Going back to the problem from earlier, let's apply the definition. In this case, the expectation that the number of rolls it takes me to roll 6, given that in the process, I roll only even numbers, is equal to the sum of all possible values of k that x could take, from 1 to infinity, of k times by the probability of x being k conditioned on event A occurring. Recall the definition of conditional probability. The probability of B conditioned on A is the probability of B and A both happening divided by the probability of A. Let's picture that within the sample space omega, we have area A and area B. Intuitively, when we think of the probability of B given A, we can assume that the outcome is within the blue area A. Then in order for event B to happen, the outcome must also be in yellow-brown area B, so the outcome must be in the intersection of these two areas. Then we divide by the probability of A to quote-unquote rescalar universe of possibilities so that the conditional probability of A becomes 100%. Applying the definition of conditional probability lets us change the conditional probability within the summation as the probability of needing k rolls to get a 6 and not rolling any odd numbers divided by the probability of A. To solve this, we first need to find what the probability of not rolling any odd numbers is. I'm going to apply the law of total probability. This gives us the probability that it took me k die rolls multiplied by the probability that all my die rolls are even given that it took me k die rolls. The probability of x equals k is the geometric variable like from the first question. The probability of k minus 1 non-6s followed by a 6. Then the probability that all my rolls are even given that x equals k is 2/5 to the power k minus 1. If x equals k, then we know that the kth die roll must be 6, so I don't need to worry about if that's even. What I need to think about are the previous k minus 1 rolls. So the exponent is going to be k minus 1. The previous k minus 1 rolls also have to be non-6 for event A, which are 1, 2, 3, 4, 5. And of these 5 non-6 possibilities, just 2 are even. They are 2 and 4. So the probability of rolling an even non-6 value is 2/5. Now we can simplify and calculate. The probability of the event of rolling even non-6s is 1/4. This also has the benefit of giving us the probability of k rolls and the occurrence of even A, which is 1/3 to the k minus 1 power times 1/6. Substituting everything back into the original problem, we have the following, which can be simplified as such. Recall that if you have a geometric random variable with the parameter p, then the expected value of the random variable is the sum of all values from k equals 1 to infinity of k times 1 minus p to the power k minus 1 times p to the power 1, which ultimately results in the reciprocal, 1 over p. Using this, we can recognize that this simplification is in the form of expected value of a geometric random variable with probability 2/3. So then the expected value ends up being 3 over 2.